This lecture is on the first derivative test and how that relates to relative extrema. So first we're going to examine this function over here and take a look at what the first derivative value would be in different places. Here we're going up. First derivative, of course, is going to be positive. This is a sharp turn, so we have a first derivative which is undefined. Here we're going down, first derivative negative. It's 0 at this point because we're flat. Positive because we're going up. 0, positive, 0, positive. Here we're 0 again because we're flat. And finally here we're negative, we're going down. So what we can see is that when the first derivative changes sign, positive to negative or negative to positive, we have a relative extremum. And note, if we don't change sign, plus 0 plus, this is not a relative extremum. So you have to change sign. It's not enough to just have a critical number, that is where the first derivative is 0 or undefined. You also have to have a sign change in the first derivative to indicate a relative extremum. And as we can see, if we go from positive to negative, up then down, it's a relative max. If we go negative to positive, down then up, it's a relative min. And so what we can do is collapse this idea down to a number line, because normally we're not going to have the function first. We'll have an equation. Obviously, we're not going to have a graph first. We'll have an equation. So what we can do is put the critical numbers on a number line. So here we have x and f prime. So x, -1, 0, 2, 4, 6 are the approximate places of these critical numbers. And then we would check in the first derivative the sign in each of these intervals and note where we have sign changes. So positive to negative is a maximum, and negative to positive is a minimum. No sign changes in here, and finally positive to negative is a maximum. So we're going to really start off with equations and get this information, which will allow us to give us the graph. Now, when we get more into trying to prepare for the AP, it's not enough to just put a number line, right, max, min, or max. You're supposed to have some sort of written statement, something like this. -1 is a local max because the first derivative goes from positive to negative. So that kind of formality. And this is a symbolic example of what we're talking about, how we need to have a sign change to have a relative extremum. F of x equals x cubed is this curve here. The derivative is 3x squared. So at x equals 0, we're flat, but clearly we don't have a sign change, positive, 0, positive. So that's not a relative extremum at 0. Okay, now in terms of shortcuts for checking derivatives, this is one shortcut we can use, and actually we're going to jump up here to do it. If we had already taken a derivative, and we had x minus 1 squared times x plus 2 cubed, we'd set it equal to 0, or see where it's undefined to find critical numbers. And it's not going to be undefined. This is a polynomial. So we set it equal to 0, and we get -2 and 1. So we put -2, and we put 1 on this number line, and I would check signs. So what you could do is you would plug in, say, something to the left of -2, like -100. -100 in here minus 1, you square it, you get a positive. -100 in here is negative, you cube it, you get a negative. Positive times negative is negative. Now you can check all of the intervals, and it's not that hard to do it, but you can use shortcuts as well. Note that because -2 is an odd root, we're going to go through. That is, we'll cross the x-axis in terms of the value of our derivative. So crossing goes from negative to positive. And here at 1 is an even root, so we're going to bounce off, so positive to positive. So therefore, the only extremum occurs at -2, and since we're going down and then back up, -2 would be a relative minimum. So now some more examples, starting off with equations and going from there. Well, before we do that, a couple more graphicals. Okay, y equals -x plus 1 squared. Note where it's increasing or decreasing. We're increasing. We use for intervals x values, so we're increasing from decreasing from -1 to infinity, and increasing from -infinity to -1. Over here, we're decreasing in this section and in this little section here, so that's -infinity to -1 and 0 to 1, and increasing in this little section here and then this part here, so we're increasing -1 to 0 and 1 to infinity. Okay, we'll start off with a parabola here. F of x equals x squared plus 8x plus 10. Let's assume we don't have a curve because this all is going to lead towards curve sketching. So what we can do is say f of 0 is equal to 10. It's always nice to get, say, a y-intercept. It's easy to do. Now let's do some calculus. Take a derivative, you get 2x plus 8. It's never undefined, so let's set it equal to 0 to find critical numbers. And we get x is -4. So what we can do now is make our number line where we have x and we have f prime. I put in 0 at -4. I check the value of the derivative on either side, so I plug in -100 times 2 plus 8 is negative. I plug in, say, 0. That's to the right of -4. 2 times 0 plus 8 is positive. And what we can see is we go from negative to positive, so therefore it's a minimum, which makes sense because we know that a parabola opening up is going to have a minimum at the vertex. And so this is about what it would look like. So we know -4 is the x value. We could plug it back in here to get a y value. So this isn't really to scale. Actually, these are by 2's. So in terms of finding that vertex, you may remember back in previous math courses, general parabola f of x equals ax squared plus bx plus c. And we want to find where the vertex is. Well, we take a derivative, 2ax plus bx, the derivative of c, which is a constant, is 0. Set it equal to 0, and solve for x. And you get negative b over 2a, which is how we found the x value of the vertex, or the equation of the axis of symmetry, back in Algebra 2. And what we're going to be getting to next section involves second derivative. If you take another derivative, you just get 2a, which indicates that the sign of the leading coefficient determines concavity opening up and opening down, which we already kind of know that that does determine opening up and opening down. Okay, taking a look at this one, we're getting into more complicated stuff now. X plus 2 squared times x minus 1. Well, before we do any calculus, we know we have x-intercepts at -2 and 1. We're going to bounce off at -2 because it's an even root and go through at 1 because it's an odd root. And we have a y-intercept at -4. If you plug in 0 for each of these, you get -4. Okay, take a derivative. Rather than multiply it all out, I'll use the product rule. So I got derivative of this piece times x minus 1 plus this piece times the derivative of x minus 1, which is 1. I will factor out the lowest power, x plus 2, and see what I've got left. And then I can combine all that together and do some more factoring. And I end up getting critical numbers of -2 and 0. So our number line, okay, -2 and 0. And we will put in our signs 0 and 0 here. And we check points to the left of -2, between -2 and 0, and to the right of 0. We plug them into the first derivative, and we get positive, negative, positive, which indicates we have a max and a min. And again, this is a cubic with a positive leading coefficient, so we kind of know it's going to do something like that, or maybe something like this. So it should come as no surprise that the max is to the left of the min. It just verifies kind of what we already know. Second derivative stuff is going to come a little later in the chapter, but that's what the second derivative number line would look like. And that's based upon this information down here. It's getting a little ahead of ourselves. So now we have x values of the max, the min, zeros. So to find y values of the max, the min, you can plug them into the original function, and you get points here, here, and here, and there's our cubic function. Okay, a couple more. X minus 1 to the 1/3 power. X equals 1 is going to be a 0. If we take a derivative, we get 1/3 x minus 1 to the -2/3. I'll rewrite it like this. And so what we see is that I have no critical numbers where the derivative is 0, but I do have a critical number where where derivative is undefined. When x is 1, we're dividing by 0. So we know that at this x-intercept, our derivative is undefined. So here's our number line. So at 1, it's undefined. If you take a number to the left of -1, -100, take a negative and square it, it's positive. Cube root of a positive is a positive. So everything's positive. To the right of 1, -1 is positive. Square positive. Cube root of that's positive. So it's positive, undefined positive. So it ends up looking basically like this. So we're coming up right in here. It's not a sharp turn. It's just that it's vertical for this moment. That's why it's an undefined derivative. And this has to do with, again, with second derivative, which is going to relate to being concave up and then concave down through here. And finally, a trig example, looked at a couple different ways. So we have f of x equals sine x cosine x from 0 to 2 pi. Using a double angle formula, you can rewrite this as half sine 2x. The derivative of half sine 2x is 1/2. Derivative of sine is cosine. But then chain rule, derivative of 2x is 2. Becomes cosine 2x. You set it equal to 0. So therefore, 2x is going to be all of these spots. I went all the way up to 7 pi over 2 because I'm going to divide by 2 now. So here are my critical numbers. So on my number line, you have to include 0 and 2 pi on your number line because those are the endpoints of your interval. So I would check a bunch of different values back in the first derivative, and I would get all these signs, and you end up getting a function which basically looks like this. If you're not happy with the double angle formula, well, there's other ways to do this. we would use product rule. So derivative sign is cosine times cosine plus a derivative of cosine, which is negative sign. That's why I've got a negative times sine. So cosine squared minus sine squared, set it equal to 0. I add sine squared to both sides, divide by cosine squared, and finally tan x is plus or minus 1, and tan x is plus or minus 1 at, of course, these same spots, pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. You get your number line. And once again, this gives you x values and max min information. To get the y values, you have to plug the x values back into the original equation.